is at the intersection of weather and climate, the NOAA Research Global Nest Initiative presented by Lucas Harris with NOAA GFDL. I'm just going to turn it over to Shira to introduce Lucas Harris.
Thank you, Alex. Yes, welcome everybody. Today, we've got Lucas Harris with us from NOAA and GFDL. Lucas Harris has been interested in weather since he was 5 years old. He is the Deputy Division Leader of the Weather and Climate Dynamics Division at NOAA's Geophysical Fluid Dynamics Laboratory. His research is focused on development and application of the GFDL finite volume cubed sphere dynamical core, which can be acronymed as FV3, to create new models for frontier weather and climate problems. He holds a PhD in atmospheric sciences and a master's in applied mathematics, both from the University of Washington, and previously worked at Princeton University and NCAR. Lucas, I'll turn it over to you.
Okay, great. So thank you, everybody. Can everybody see my slides okay?
Yes, we can see him.
Okay, fantastic. Okay, so thank you so much. First of all, I want to thank to all of our collaborators across a number of different institutions, both inside and outside of NOAA research. Okay, and here I'll get started. So NOAA's mission includes a very long range of modeling problems from minutes to millennia, I like to call that. And NOAA has unified around 2 different modeling systems for their ongoing applications. The first is Unified Forecast System, of course, which is really starting to get to be an exciting time for the UFS with the HASS going into operation soon and the great advances made in the GFS, GEFS, and RRFS. We also, in GFDL, we have the seamless modeling suite, principally of climate models. By some measures, these are some of the best IPCC class models in the world, especially in terms of extremes variability in the Earth system. And now these 2 systems span a very broad range of applications, but they are unified around a relatively small number of key community components. And I'll discuss a little bit more about how these components tie into all this. The question is that with the successes in the systems and the ongoing development of these, where are the next scientific areas that we can go in to develop these models? So anyway, starting in FY22, Congress directed the NOAA's Climate Research Labs and Cooperative Institutes, the line item in the budget, to initiate the development of a global nested high-resolution atmospheric model as part of a climate change adaptation and resilient infrastructure. And as a result of that directive, the NOAA Research Global Nest Initiative was formed in 2022, last year, to carry out this directive as a multi-institution collaborative effort, leveraging existing development within the UFS and the GFDL seamless modeling system. So the goal of the NOAA Research Global Nest Initiative is to develop these, what the verbiage as I could use it is a holistic, seamless digital twins of the Earth system for prediction, projection, and understanding of extreme weather events and to create actionable information at all time scales. So the 3 principal goals are to create these digital twins, to create this actionable information at all the time scales involved, and to also directly feed into development of the UFS and seamless modeling system. And towards that effort, 3 main research products are going to be developed. One is a global nested medium range and S2S prediction applications, eventually 6 kilometers global, 2 kilometers nested over the contiguous United States or tropical oceans. Another is a kilometer scale global storm resolving model simulation, and which I'll sometimes refer to as K-scale. And also to start going into the sub-kilometer with multi-nesting and with our doubly periodic process models.
Lucas, sorry to interrupt. I don't think your slides are advancing.
Not advancing? Okay, let me try to share again.
Okay.
So, okay. How's that?
Okay, yeah, there we go.
Okay, all right, can you see that going back and forth? Can you see that going back and forth?
No, we don't see that going back and forth.
Okay, let's try that again. Okay, so this is the window that's being shared by a GoToMeeting, right? So
yeah,
let's see here. Okay, so here, let me turn Okay, so showing that application. Okay, you see the wind. Okay, do you see the window moving now that way?
Yes,
move
we
it back
do.
and forth.
Yep.
Okay, great. Okay. Anyway, so let me try presentation mode one more time. Okay, now do you see it going back and forth?
No, it looks like presentation mode isn't working for some reason.
Okay, I apologize for that, everybody. So here I can do it this way. Okay. Anyway, so yeah, unfortunately the animations will not work, but I can do this. So okay, thank you, everybody. Apologize for the technical difficulties. So the foundation of the Global Nest Initiative are these 4 key technologies, some of which are more familiar and widespread, some of which are relatively new. And I'll describe each one of these in a little bit of detail as I go on. So the most familiar of them is FE3, the GFDL finite volume cube sphere dynamical core, as we already heard. I've already done a number of different tutorial presentations on FE3. So for more details, you can go to those on the website that I'll mention here in the next slide. In the meantime, I just want to give you a brief rundown. FE3 is the fluid solver, or the dynamical core, for a community of atmosphere models, both here in the United States and NOAA, NASA, and elsewhere. For a very large federated community of models. You have this one dynamical core that's very flexible, very adaptable, and can be used for a very large number of different applications. So, and it was built for these purposes using accurate numerics, computationally efficient as possible without compromising the scientific integrity. There's one of SJ's favorite quotes is that a good model must be a fast model, and a flexible solver and interface, so it can be implemented in a large array of different models. And what all this gets you forecasts that run on time, development that's faster, you can run the model more quickly and reiterate more quickly, push to ultra high resolution with the computing resources you have, and again, the large array of applications. Here's a famous one, the NASA GEOS model, which is the original application of FE3 and FV, in fact. So here's a nice example of what you can do with that.
Lucas, so sorry to
yes.
interrupt one more time. I'm hearing in the comments that some people are seeing it cut off on their screen. Do you want me to go ahead and share the slides and just advance them for you?
Yes, if you go ahead and do that. Okay. Sorry for everyone. Oh, what? Yes. Okay. Okay. So here I stopped sharing the screen. So let me hide that.
All right, and we were on slide 6. Can everyone see my screen?
Yep. Okay.
Okay.
Okay, great. All right. Can everybody see that okay? All right. So next slide, please. So over the last few years, we've greatly expanded our community-facing resources and the FE3 team. We've developed a FE3 portal here at this website here, which is a center of information, a more general information about FE3. Includes publications, scientific documentation, tutorial links, use cases, and more information. So in one convenient place. We also have the community GitHub website which is the official repository for our code, and for both our development as well as the climate model development and for development within the UFS. We have this official site for official releases, examples, documentations, issue tracking, and much more, including pull releases. I've had a number of different pull releases that were approved today, in fact. And these are probably the best places to start if you want to learn more about FE3 itself. So next slide, please. Okay, and one of the things, I don't mean to get real deeply into the weeds with regards to FE3's powers, but I do want to show one thing in particular that shows off really one of the strongest features of FE3, and that's its representation of vortical modes. And one of the most noticeable things about any fluid from galactic flows all the way down to swirls in one's coffee cup is that they spin, they form vortices, they rotate, in short. And FE3 is designed to have an excellent representation of these vorticial flows. And this is true at all scales in the atmosphere. On the left here, you see a fairly famous example. Originally, GFDL had developed this very good CM 2.0 coupled climate model, which had a number of great features, but it still had this persistent problem a lot of climate models have, in which there's this spurious heat uptake that was related to a incorrect location of the mid-latitude jets. And this may not look like a big shift in the jets, but it turns out this has a big impact on how much heat the ocean takes up, and that's a big problem for long-term climate simulations. So then came along S.J. Lin, and he worked with a team of engineers to put the latitude longitude FV, this older predecessor to FV3. When this was put in, this took about a month, the jet shifted to the right place, and this provided an excellent heat uptake simulation and control climate integration. And this turned CM 2.1 into the best climate model of its generation. So this is really an astounding work. And the reason why, one of the reasons why you can trace this is that that's an eddy-driven jet that was shifted to the right place. That is due to vorticity dynamics. And that's one of the things that FV and now FV3 has really allowed. But you can go to very high resolutions. You go to the kilometer scale. This is a 3-kilometer simulation from Sea Shield, a 3-kilometer US nest on the right. And you can see very fine scale representations of rotating updrafts that are related with severe thunderstorms. So you can see very fine scale representations of hourly maximum tracks. These are an hour's tracks of severe storms during this outbreak back in 2017, where you can see these very fine scale representations of the rotating updrafts. So rotation is a great example of the value of something that can give you simulations at very coarse resolutions and very high resolutions. And one of the real keys to that is a good representation of these rotating features that really dominate fluid modeling at all scales. Next slide, please. Speaking of rotating systems, we have also developed some seamlessly integrated idealized examples within our frameworks, our modeling frameworks. FV3 has some capabilities to do idealized convection and radiative convective equilibrium simulations. There's an example here on the right. This is a really neat example. We're finally writing this up, of tornado-like vortices in a idealized super stretched global model. I say tornado-like because, I mean, they're larger than an observed tornado, but there are the same dynamical processes that are giving rise to these. You can see the vortex tilting and stretching and all that. And furthermore, you can take a look at our doubly periodic domain to run radiative convective equilibrium, large eddy simulation type runs. This is a number of different papers and published on this, going all the way down to 62.5 meters, in which we trace convection down to its level of convergence, which is defined by George Bryant at NCAR at about 250 meters. So there's and again, this is all integrated within the same modeling systems. This can be done within, within the UFS, within the seamless modeling system, seamless modeling suite, and all that. So this is another example of seamlessness that FV3 can give you. Next slide, please. And finally, about FV3, I want to mention all the different ongoing developments within FV3. And I don't mean to go through every single one of these in detail, but this is just a sign of the vibrance of the worldwide FV3 development community. There's a large community of people who are adding in new features and have been able to understand the codes to be able to help advance the science of each individual modeling system and for the whole community. And I like to quote my retired colleague, Morris Bender, in this case. He's the one who led development of the operational GFDL hurricane model for many years, the predecessor to WRF and HAFS, or excuse me, predecessor to HWRF and HAFS. And simply he said that, key element to making collaborations work is having individuals who enjoy working together and are able to do so. And the way I like to say it is that one of the best things about working in NOAA is I get to work with all these scientists from the community who are some of the best people in the world at what they do. Next slide, please. So moving on, I want to discuss a little bit about SHIELD, which is our system for high resolution prediction of Earth to local domains, which is a seamless integrated system for that can be configured in a whole lot of different ways for different applications on weather to S2S timescales. And here I show a bunch of different configurations, many of which I'll talk about over the course of this webinar. I don't intend to go into every single one of them right now, but I will give an overview on them later. Next slide, please. And the kind of governing idea of SHIELD is that we have a simplified system that can represent within one code, one executable, one workflow, all of these different all of these different applications, from S2S prediction all the way down to very short range severe weather prediction. And this system shield, it takes advantage of the simplifications here. And this is not, and this is something that's being followed by some other modeling systems as well. I think about the Department of Energy's SCREAM model, their new global model. And this allows us to be able to develop new things relatively simply and take advantage of advances in one configuration that can be applied within other configurations, and then can spread within the UFS and the seamless modeling system within which SHIELD is unified with. And it also gives us a way of demonstrating new capabilities within FD3 and within the physics that we've developed and that our colleagues within the broader community have developed. Our physics here are an extended version of the GFS medium range weather physics. And I mentioned that we can seamlessly move innovations from one of the configurations into other systems. I prefer this as kind of a holistic seamlessness. And furthermore, these gradual implementations, the gradual innovations, as well as the yearly updates, you keep incrementally adding in new things to this modeling system. You're moving between the configurations. This really gets at this one quote, another quote that I like. From this technology blogger. It says that incremental improvements over a year turn into profound improvements over 3 to 4 years. And we will see several examples in which we've made a lot of different small improvements year over year that can really add up. And we are able to submit this to a variety of intercomparisons and test beds. Next slide, please. Here's one example of this. This is part of a collaboration that we have to help improve hurricane microphysics, multi-center again, with GFDL, AOML, PNNL, the DOE laboratory, and the Hebrew University. The basic idea there is that it's leading into a project to use observations within hurricanes and bin microphysics to improve the representation of microphysics in hurricanes. And we can broaden that out a bit. We've used that to develop a new version of the GFDL microphysics, version 3. And this is applying climate thinking to improve weather forecasts. And this is an example here. We published this in James last year, in which we improved the microphysics and we improved the liquid water path root mean square errors. And that has led towards improvements in the root mean square errors for 500 millibar height and 700 millibar temperatures. So this is one example in which by improving the clouds and radiation, you can use that to further improve your prediction skill scores. Next slide, please. And here's a little bit more out there idea, and this is one of those examples where we're able to, where we have the privilege of being able to take on a sort of a more ambitious research program. This is called the FE3 Integrated Physics, which is a complete reimagining how physics and dynamics and CUP are integrated within modeling systems. And this is sort of a more holistic way of doing it, compared to the existing mix and match that has been driven by some popular modeling systems. This reimagining allows you to put the physics embedded within the dynamical core itself. And this gives you a lot of advantages. It gives you consistent energetics, thermodynamics, and computational loading, while also allowing you to call the different physical parameterizations at correct timescales. So here's our notion of an eventual overall integrated physics within SHIELD. And you can see that the inline GFDL microphysics, one example of integrated physics, which we call it within the dynamical core, compared to the split out microphysics, can give us considerable improvements in ACC and in root mean square error for weather forecasts, as well as some improvement to biases in some cases. And this is the foundation we're building towards the next step, which is a 6.5 kilometer global SHIELD. Next slide, please. And so where is all this going? And one of my favorite examples of how SHIELD development has been able to improve operational modeling is, and this an example of a great early success for NGPS and the UFS, has been improving hurricane forecasts. And a few years ago, we published a paper. We were collaborating with the European Center. And what we did, what our colleagues did, is that we took the legacy spectral US GFS, and we took a look at the tropical cyclone tracks in that. This is a plot of error, lower is better. And we compare that against the same runs using the same initial conditions in GFDL SHIELD. And we found that using the better model was able to get us lower track errors. So then we took the European Center's initial conditions and we implemented them in SHIELD. We ran with that and we were able to get better forecasts still. In fact, we got lower errors than the European Center did, which is a world leading hurricane track forecasting model at the time. So this is transitioned into NOAA operations, and with a lot of work led by the Environmental Modeling Center, Fenglin, June, and Daryl did a phenomenal job implementing the new GFS with FE3 and a lot of other applications, improving the data assimilation. And indeed, for the last couple of years, the GFS has caught up to, and in some cases is actually beating the European Center in Atlantic tropical cyclone tracks. So it's a really remarkable achievement. And I believe this is the first time that the GFS has been the world's leader. They were leading the world in 2021 for tropical Atlantic TC tracks. And we can do even better with that with some of the more recent improvements within SHIELD. So this is a really very powerful thing. Next slide, please. Moving to more technical things, I want to discuss a little bit about the flexible modeling system, FMS, which is a combination of a framework and libraries. And now any modeling system that's using FE3 or MOM6, which includes a lot of things, that includes the UFS, Seamless Modeling System, GEOS, CESM, and many other things, they have picked up the FMS libraries, even if they haven't picked up the entire FMS framework. So FMS is under the hood of a lot of different modeling systems, and there's a lot of power that it gives. Now we can go take a look at what FMS gives us in terms of scaling with the FE3. This is a result from 11 years ago, scaling to over 1 million threads on Argonne's massive Blue Gene Q system. And we were able to take an early global storm resolving model, the HIRAM 3.5 kilometer model, and we were able to scale it out to about 85 days per day. And the scaling was fairly linear out to a large number of cores, which is a pretty big achievement for that time. Now you can go to the present day. We have a new partition on Gaia where you can scale out to over 200,000 cores. And my colleague Rusty Benson has been able to do some scaling tests with the Solo Core FE3, and he's got it to scale out pretty close to linearly all the way to filling up the machine to the point where we can actually meet the operational requirement of 8.5 minutes per day with this model on the system. Now, of course, we got to fill the whole thing up, which makes it a little bit impractical for day-to-day weather forecasting. But this shows that, yeah, we may be able to get to the point where you can run a 3-kilometer global model routinely in real time within the next half decade or so. Next slide, please. But going even beyond that, so one thing that people have been saying for about 10, 15, maybe even 20 years is that eventually the CPU and MPI era is coming to an end. And it hasn't ended quite yet. I mean, we've just NOAA's gotten several large CPU-based supercomputers lately. But we want to be ready for the transition to graphical programming units. And we collaborate with our partners at the Allen Institute for Artificial Intelligence. And what they've done is they take this community system called Grid Tools for Python, GT for Pi. And that's a domain-specific language, which means that you can rewrite the model in Python, which is an interpreted language, but then you translate that to compile it into optimized code for any given processor. And this allows you to have one powerful code, one code which is efficient on a whole variety of different systems, whether it be CPUs or the various GPUs that are out there. There's a fairly large community around this. It's already used in operations of Medo Swiss, MPI, and the European Center are both looking into using it. What the Allen Institute did is they led implementation of what was originally called the FE3 GFS, FE3 plus parameterizations, into this language to create this what's called PACE, which is this ported system that can be performant on GPUs. And porting into Python gets you a lot of advantages for new science, new diagnostics, instrumentation and application, like the AI or the machine learning I'll talk about later. And this has been transitioned into NOAA and NASA and is now being SENA funded both here at GFDL and GSL. Next slide, please. And just to show some of the results from this, they were able to, our partners at AI2, they ran PACE, the dynamical core with microphysics, and they were able to get a strong scale out to the size of this entire large supercomputer at PIS Diane in Switzerland. And for the socket-to-socket comparison, this is a truly fair comparison. I see some of these kind of questionable comparisons of core to core, which aren't quite right. They're able to get a 2.28 kilometer FE3 plus microphysics, the PACE system, to get about 0.12 simulated years per day, about 1.5 months per day using 2,400 nodes on this PIS-DI8 system, which is about 4 times faster than the Fortran code at the same resolution. And with this is with their kind of older P100 GPUs, so the newer A100 GPUs, which is what DOE's Perlmutter machine uses, we can actually get a 8.5x time speed up. And there are promises that we can do further optimization even beyond that. And I have a little rabbit there to say that we've turned our powerful truck into a real hot rod. Next slide, please. So I talked about a lot of the technology. Well, what all of this is good for? I mean, yeah, so we've all seen technological demonstrations that aren't useful for much. And our goal is to really take this global nested model and do something, well, at least I can do something pretty neat with it, I think. Next slide, please. So we've been working on nesting within FE3 for a little over a decade right now. And it's starting to become a really mature technology. And indeed, for the first day that the Global Nest Initiative was funded, we already were able to produce results using our global nested systems. And one of the big advantages is that with this nested global regional setup, you can do extended range convective scale prediction that currently is limited to 1 or 2 days in a lot of regional models. And here's a couple of examples: 3-kilometer nested T-shield over the tropical Atlantic, C-shield over the contiguous United States, as well as some new applications, the multi-nested teleshield going down to 1.4 kilometers over a small region, like the Northeast Corridor, or over Taiwan and its surrounding oceans. This isn't the only variable resolution option in FE3. We also have this very powerful stretched option, which GEOS and GeosChem are using. There was a talk about that last year. Also, advances in these systems directly benefit and inform the whole variety of convective scale applications using FE3, including we've had excellent collaborations with the HASS and RRFS folks on this issue, on using what we've learned from our global nested setups for their operationally ready nested regional systems. And HASS is about ready to go on operations, and RRFS is doing some really amazing things. So we're really excited to see where this can go. Next slide. A little bit about our C-shield nest. So we see that this nesting is able to extend severe storm prediction into the medium range beyond days 1 and 2, and start to get predictions of severe weather or severe storm events out to days 2 and 4 and out further into the medium ranges. So here's an example from an earlier paper in which we see the surrogate severe score, a common means of verifying a severe storms forecasts, are showing similar skill on days 2 through 4 as they are in day 1, which itself is a nice improvement. And one of the things to start to think about is that can you get better medium range skill? And as I showed earlier, improvements of clouds and radiation, especially things like stratiform cloud and anvils, as well as shallow convection and in the land surface model, can give you improved 500 millibar skill. In fact, this is a change from the red line, the 2020 version, up to the blue line, the 2021 version. That gives you the potential for skill out to the 5 days and even longer. One really cool thing I want to point out, we are collaborating with our partners at NCAR, and they have a C-shield ensemble ready to go to submit to a next month's spring experiment. And they've put together this really cool ensemble based on their earlier ensemble work using C-shield, and I'm really excited to see what they can do with that. So next slide, please. Another thing that is both a nice forecast application as well as some really interesting scientific possibilities is the global nested T-shield for hurricane forecasts. And hurricanes are unnatural because they interact strongly with their more broad scale environment. So the global nest is a real nice test bed for that. And I'm showing an example here. With this multi-nesting, with the global regional nest, we can get very good track errors with this nested model on par with what we can with the global model, the global uniform resolution shield. And this has been a really nice testing ground for showing how explicit deep convection on a large 3-kilometer domain can control intensity, synoptic steering flows, and curvature and tropical cyclone structure. And it's also a neat testing ground for testing how explicit convection interacts with the larger scale, the synoptic and global scales, as well as the role of parameterized shallow cumulus. So next slide, please. So one example we can do with that is we can take the new positive definite scheme that's been implemented within FE3. It's now a few years old, but we did this nice study where we took a look at tropical cyclone structure with the positive definite scheme compared to the older, more diffusive monotonic scheme. And not only were we able to improve tropical cyclone structure by allowing more water vapor into the eye wall, which improves the updrafts, the intensity, but it also shows some promise for predicting a rapid intensification. And here's a few examples of that from a few years ago. So this shows examples of where we can leverage our advances in the numerics to be able to improve predictions of these very challenging events, as well as going to the next level of tropical cyclone forecasting into predicting structure. And indeed, we have a project here to be able to study the structure of a post-landfalling tropical cyclones using this existing theoretical apparatus and combining it with data to be able to really understand what happens to tropical cyclones post-landfall and how well our models are simulating it. Next slide, please. And this, the fact that we're using a large 3-kilometer domain, and this will come up again in the context of global storm resolving models, is that we have been able to turn off deep convection on these domains. And we have explicit deep convective parameterizations. We're kind of marginally resolving them. So remember that you're not really resolving convection until you get down to about 250 meters, at which point you're truly being able to represent things as something more than just a grid point, just a single grid column. You can represent convection as a larger scale, as a coherent feature at these resolutions, but only a marginally resolved one. And the problem with using explicit instead of parameterized convection is that you can't just tune your explicit convection to get you the circulations you want, which is something that we've done in global models for years. So this becomes a lot harder, and the dynamics plays a big role. So here's two examples where we use two different convection schemes. Not convection schemes, advection schemes in the dynamical core. We find that using the less diffusive advection scheme gives you more intense, more widespread convective cells. And this has direct impacts on tropical cyclone track forecasting. We see that the change in convection changes the synoptic scale steering patterns. And that those steering patterns then affect, well, how do they change the direction of tropical cyclones? They have direct impact on how well your tropical cyclone track predictions are. And we only see this at 3-kilometer resolution when you have explicit convection. At coarser resolutions, you don't see that kind of dynamics dependence. So this is a kind of emerging issue that you get when you are using these large convective scale domains. Next slide, please. Now here's something I'm really excited about. So I went to the European Center a few years ago, back in before time, and I met Tim Palmer. And he's told me that if I wanted to improve S2S prediction in the United States using nesting, what I should do is put a nest over the maritime continent and try to improve the MJO. And now our models here at GFDL get pretty good predictions of the MJO already, even at fairly coarse resolution, but higher resolution does give you better forecasts. And here's an example of that. This is a collaboration that we have with our partners at AOML, originally funded by the Weather Program Office. We did a number of 40-day runs with our nested grid over the maritime continent and compared it without runs without the maritime continent nest. And we found that with that nest, we're able to extend our useful prediction skill of the MJO all the way out to 39 days, which I believe is longer than any other model. And this is during the dynamo period where the MJOs turn out to be fairly difficult to predict. This model is not prohibitively expensive. You can get 40 days in 8 hours at 4,000 cores on Gaia. And it turns out that the real benefit of the enhanced resolution is that you're improving the precipitation and the diurnal cycle over the maritime continent by going to this higher resolution there. And that's truly kind of the key to getting good propagation of the MJO out through the nest and out into the larger global domain. So we're continuing to work with our AOML partners. They did a fantastic job with this to be able to see what the impacts on weather over the United States might be from this. Next slide, please. And then beyond that, we can start to do S2S predictions of a severe storms forecasts. This is an example of a slightly lower resolution 5-kilometer nest, still good enough to give you explicit severe weather in the contiguous United States. We did 30-day runs of this during a number of different springs over 6 years. And, excuse me, this is 5 years, excuse me. And we were able to do the same surrogate severe forecasts on regions, not just on an 80-kilometer grid in this case. And we find that using categorical measures of skill, we can find promising skill, especially over the northern United States, the Midwest, the northeastern, northwestern United States. We find promising skill all the way out to weeks 3 and 4, which is an interesting application. And we have now a collaboration with our partners at the National Severe Storms Laboratory, and they are going to take another set of simulations we're done and start to evaluate cold season severe weather outbreaks, which there might be more potential predictability for these sorts of events. Next slide, please. And finally, I want to talk a little about the global storm resolving model we've developed called the X-Shield, which itself is a major pillar of the global nest initiative. Next slide, please. So the X-Shield is the latest in a long line of FE3-based global storm resolving models that have been developed here at GFDL and at NASA. This is a X-Shield itself, 3.25 global model with no deep convective parameterization, and you see on the upper right-hand corner this beautiful -5/3 kinetic energy spectrum with this almost perfect 4 delta X cutoff, as well as the excellent tropical variability you see in the lower right-hand column. You don't need 3 kilometers to get a good MJO, but you can still get some really nice stuff from this. This is also a fairly efficient GSRM, although even the most efficient global storm resolving model is still going to be pretty expensive, as I said earlier. And the data has been used for a number of different projects. It's been submitted to the Diamond Intercomparison, and data is slowly becoming available through the public NODD repository. And one of the kind of guiding principles of developing global storm resolving models is this quote from Suki Minabe, one of the inventors of the climate model, who won a Nobel Prize a few years back and worked here at GFDL for many, many years. And the way that he liked to put the push to develop these kilometer scale models, global storm resolving models, is that if you keep increasing resolution, but you don't make the model more complicated, I think you will have a great time. And Suki really kind of enjoyed the whole practice of developing global models like this and the climate models that he developed for many years. And I think having a great time is a really excellent way of putting it that I'll come back to a little later. Next slide, please. Okay, I don't want to dwell too much on this. We've been able to do years-long simulations on Princeton's Stellar supercomputer, which is funded by NOAA. And we've been able to do years-long simulations. And the nice, interesting thing about that is that even without a deep convective parameterization, we are able to get a useful mean climate, which itself is a pretty interesting thing. We're able to represent the mean climate fairly well, on par with a lot of the very highly developed IPCC class models. So that gives us a very good foundation for doing some of this other work that can take advantage of the higher resolution. Next slide, please. One of the things we can do with X-Shields, we can start to do warm climate integrations. We have some computing power that allows us to do that. We can only run a few years in a warmed climate, but this is enough to start to really think about what can we do under global warming when we start to explicitly represent convection worldwide. I don't believe anybody else has done these sorts of long warmed climate simulations before anywhere on Earth with any global storm resolving model. So we've been able to do these simulations in a couple of different warm climates. Here's an example with a +4K SST. This is without the increase in carbon dioxide. But we can do some interesting work with this, and indeed we find from this experiment, and I should warn you, only 1 year simulation is being shown here, so there's still some variability on this, but we see that continental convection is shifting to higher latitudes, which has some interesting implications for extreme weather, as well as for precipitation and hydroclimate. And we're able to explain this through large-scale circulation shifts, as you might expect, not necessarily by changes in CAPE. So we've got this nice data set. We're doing some interesting stuff with it. With our collaborators at Princeton and as part of the NSF-funded PIRE-CIRRUS project. So we're going to take a look at convection, precipitation, and clouds with these warm climate simulations. Next slide, please. Here's another example. This is the NOAA-funded U.S. hydroclimate project, Western U.S. hydroclimate project. And one of the things that I would like to discover in the way is that it's relatively easy to get better results in complex terrain by going to higher resolution. I like to put that as resolution is paramount when it comes to orographic precipitation. And here's a couple of examples of that. We compare a very good 50-kilometer model, AM4, to the precipitation change in a +4K simulation. We find that there's interesting changes in precipitation, but they're in Central California, upstream of where the mountains actually are. And if you take a look at X-Shield, the 3-kilometer model, we see the precipitation under warming is in the right spot where you see the mountains. And so that itself shows some of the value of going to increasingly high resolution. And another value, so we can think about, well, what's snow going to do under a warmed climate? And a lot of models suggest that it's all going to melt out, but they can't represent the high mountains where a lot of the snowpack is. X-Shield can represent the mountains up above the snow line, and suggest that California might be able to hold on to its snowpack into the 21st century and beyond. Now, of course, there's a pretty big error bar on this. It's only 3 years of simulation in this case, but can't show you what you can do with the global storm resolving model that you can't do with some more traditional models. Next slide, please. Another thing you can do with the global storm resolving models, you can feed those hungry machine learning algorithms, because you got a lot of data to pipe into a machine learning system. Our partners at the Allen Institute, again, have developed a hybrid modeling system. They took the proto UFS, the FV3 GFS, and they are able to do this corrective machine learning on the system, which they published several papers about already, which have been trained on our 3-kilometer X-Shield output. And when they do the machine learning corrections in this 200-kilometer model, which is about 1,000 times or 10,000 times less expensive than X-Shield, they're getting some pretty astounding improvements. They're able to eliminate the bias in land surface precipitation, land surface temperature, and be able to reduce the error quite significantly to the level where it's on par with the IPCC class simulations. Again, in a relatively very cheap model, which then you can think about what sort of climate impacts simulations you can do with this sort of thing too. So yeah, again, they're doing some awesome work with this. Next slide, please. And then briefly, I want to touch on some of our team's work on sub-kilometer and towards sub-kilometer modeling. One of the neat things you can do, again, is you can use the multi-nesting in our teleshield to get down towards 1.4 kilometers and then even sub-kilometer resolution. We are testing a real-time implementation of this over the Northeast corridor to really be able to get some of these hyperlocal impacts from severe weather. And furthermore, you can use our process study framework to start use a simplified FE3 for radiative convective equilibrium. This really cool Giga LES simulations pioneered at NCAR and at PNNL. And process studies as well. Here's another example that's just published, again, down to 62.5 meters, again, within a radiative convective equilibrium simulation using FE3. And we're also starting to look into large eddy simulations. We have a multi-center collaboration on SGS turbulence schemes, which has been funded by the Joint Technology Transfer Initiative, to be able to implement this within the UFS and more closely within the FE3 numerics. Next slide, please. And finally, to conclude, I want to just give a couple of summarizing notes. First of all, I've talked a lot about the global nest, which is within FE3. There's a lot of possibilities for efficient global to regional variable resolution simulation down to convective scales and beyond. The results that we've shown show that storm scale and K-scale climate modeling, which I was told would be something that would happen maybe in my lifetimes when I got to a very old age, and I don't feel that old quite yet, but yeah, storm scale climate modeling has arrived and we're able to do useful things with this today. Also, I've shown examples where across a number of applications, really year-over-year improvements add up, and indeed the recent successes in the GFS's hurricane simulations is a great example of that. We also see that also in HASS, RRFS, and a very big variety of other applications too. And finally, I'm going to steal a quote from Richard Feynman and say that there's lots of room at the sub-kilometer bottom, in which there's a lot of space to grow for new applications if we go below 1 kilometer that can be done within the UFS. Again, it's not something you just take out of the box and run. It'll take development work, but there's a lot of cool things that you can do. Next slide, please. And this is my last slide with content. And after this, I've had some thoughts about what the community could do, what the community and the broader, just kind of the broader modeling initiatives out there can really do. One of the things is realize that NOAA provides an enormous amount of data from the modeling systems, the observations, all for free. And in particular, the GFS is the world's leading modeling system where end-to-end everything is free, from the input data, the modeling system, data simulation system, and all the model output. It's all available out there for free. What can we really do with all these massive resources? And one of the things I was thinking of is the science of medium range variability and predictability, which I know that's been, a lot of this work's been done in Europe. There hasn't been so much work here in the United States, and it'd be exciting to see what people can do with the new modeling sets that are out there. Furthermore, I encourage people to think holistically, both in terms of model development and in analyses. Being able to work with a unified system like the UFS allows us to have this kind of seamless holism going between different applications. The example that I'd like to think about is, what are the upscale impacts of explicit convection, both in the regional domains, the large regional domains like the RFS, and in things like the global nest, global storm resolving models, or the big diamond data sets you can look at for that as well. And think about what explicit convection can do to synoptic and planetary scale circulations. And then just keep another kind of, I don't want to call it challenge, but motivation is to get better. Just keep trying to raise your standards and keep trying to beat the bars you keep setting. This is sometimes called the drift to high performance, as contrast to the one of the systems traps called the drift to low performance. And I think this is really a great driving fact that we see time and time again with models. You just keep trying to raise the bar over and over again, and get better and better. And finally, to take the quote from Suki, let's have a great time. And to some extent, model development sometimes is seen as kind of this grim and dull, technical, and not even technical, just kind of a turning the crank endeavor. And really, I think all this, from the technology to the science, is really just an amazing thing. I mean, there's this amazing system that NOAA and our community partners have. So what can we really do with this? It should be an amazing thing. What kind of great things can we do with this modeling system? Next slide. And finally, and I know I keep stealing quotes, here's one from Steve Jobs. Finally, I want to thank both S.J. Lin, the creator of FE3 and the originator of SHIELD, and the FE3 team here at GFDL, as well as our wonderful community of partners, both inside and outside of NOAA. And again, as I said, this is one of the greatest things about working at NOAA is I can work with some of the people who are the best in the world at what they do. So anyway, thank you. Thanks for everybody's time. Thanks for hanging in there through our technical issues. I'll stop there and I'll take questions now. Thank you so much.
Yeah, thank you, Lucas. I put this document in the chat if everyone could go in and throw some questions that they have. Lucas, can you see this screen, or do you at least have access to this document?
Yes, I do. So let's see here. I see chat and I see the question. Yeah. So I see the document there. Okay, I see anonymous dinosaur and anonymous llama. I like the animal themes that the G Suite does.
Yeah.
Okay. Okay, so thank you for your updates. I understand that nesting is limited within the global tile. If we want to refine maritime continents simultaneously with the CONUS, it will not be possible. Okay, actually that's with the current FE3. That is a fantastic question. Thank you for asking that. And indeed, some of the earlier versions of FE3 only had the capability to do one nest within the global domain. But thanks to the work that's funded by the Hurricane Supplemental, Joseph Moelan, our computational scientist, did implement changes in the public releases of FE3 that allow it to do multi-nesting, telescopic nesting, and nesting in the regional domain. So those are all capabilities that are out there. And in fact, HASS is making great use of the regional nesting already, as well as the fantastic moving nesting that AOML and EMC has put in together. So it is possible to do that right now. So, but thank you for bringing that up, and I'm glad that I had the opportunity to discuss that. Thank you so much. Okay, and in fact, here's another excellent question related. Can you have a nest with a lower top than the global model? And the answer is yes. In fact, out of the box, FE3 supports what we call vertical nesting. You can choose a different number of vertical levels on both domains, both the nest and its parent. The nest has to be at the same level or lower than its parent, but we can do vertical nesting within FE3. So that is a capability that does exist. And don't need to do anything special. Just choose a different NPZ and NPZ type on your nest. So yeah, thank you so much. Okay, and so here's a comment from actually from Rusty. It sounds like the FMS infrastructure library can support a nest spanning tile faces, just not corners. The object need be added to the FV3, and indeed that is indeed correct, Rusty. That's a good point. FMS, the libraries do support nests that can go across tile edges. Corners is too difficult because that's where you have the singularity, and that's where you have a lot of these topological difficulties. My mathematics isn't good enough to figure out how to do that, but it is something that we could implement within FV3. So that's an excellent point. Thank you, Rusty. Okay. Do we have any more questions? Okay. Do we have any questions from the room? No. Okay. Great. All right. So I'll see here. So I'll give another minute for any more questions.
Looks like there was a question on number 3, I see.
Okay. FV3 clearly has many capabilities in the publicly released UFS applications. How do you see the possibilities to transfer these capabilities to the UFS applications? So many of the things that I talked about actually do exist within the UFS already. So like I mentioned the nesting capability, the stretching capability, that all exists within the public release of FV3 has been implemented within the UFS. And there are a couple of things that we are working on. One of the big things is the integrated physics right now. We are working with our partners at, I believe it's, what is it, DTC, on being able to integrate, on being able to have an integrated physics driver that can interface with both CCPP and our own integrated physics. So that is something that is forthcoming that we are partnering with. The other thing is to implement the workflow within the UFS for the global nest, and that is actually something that we have money from. We have some funds from what is it? The Hazardous Weather Test Bed, and our partners at NCAR to be able to implement within the medium range weather forecasting application. So that is something that is coming soon. But the capabilities are principally already there. It's just a matter of coming up with a configuration to be able to execute it. So thank you so much. Okay, what would be included within the nested workflow? So the really kind of neat example we'd like to do is have a workflow where you can run a global domain which uses the GFS configuration, and then the nest that uses the RFS configuration, or perhaps the HAS configuration if you want to do tropical nesting. I was informed that unfortunately CCPP doesn't quite yet support that. It is supported in the older IPD simply because we can just turn on and off these things. But that's the big thing, is that we'd like to be able to do that. The implementation isn't going to be anything that's going to be particularly radical. It's just it just takes somebody to actually just set it up and be able to get it to run nicely within the existing workflow. So thank you. So another question, the capacity for SHIELD to run kilometer scale global experiments at annual timescales is amazing. Oh, thank you so much. Is there any plan to perform more conventional climate experiments like 35-year AMIP? It'd be really cool if we could run a 35-year AMIP simulation, but unfortunately we don't quite have enough computing power to do that. But I mean, we do want to do a multi-year AMIP type simulation, which is one of the things we're looking forward to, maybe in the next version of XShield. And I think maybe something that could just follow a whole ENSO cycle from an El Nino to a La Nina to give us a warm period and a cool period would itself be a pretty powerful application, and maybe focusing on a satellite time period. Yeah, and in fact, we're currently kind of limited to, in fact, we are limited to the 2010s. And if we could, we'd like to be able to do a longer time period from that time period. I know I have Graham Stevens here visiting today, our lab does, and he's interested in that. But we would definitely like to be able to push this towards a longer time scale to really see what sort of applications we can put it to. So thank you so much. And of course, yeah, better comparison to satellite observations. That itself would be a very powerful thing. We're looking for more applications, and really would like to be able to push that into higher resolutions too. Okay, longer time periods, excuse me. Okay, and okay, I see we have a bit of a discussion also going on about coupling. and worked out how the atmosphere nest should be coupled to ocean and ice. And would the ocean see the input from the global courser from the nested high resolution run? So that is actually an interesting open question. It may depend on whether you want to nest to a couple, if you want to couple to a nested ocean as well. The way that we did it in the older HIRAM, we did nesting within HIRAM, is that the coupled land model saw only flux coming in from the high resolution nest. So we were only able to run a single uniform resolution land model, and it saw inputs coming in from the nested grid itself. Now we can run with the nested land model as well in like AM4, but there is some ambiguity in how best it can be done, and that may necessarily be left for development. But thank you for asking that. That's an excellent question. And as Rusty points out, it would require one to have a good exchange grid as well, which itself is a bit of a challenge. So we have about 1 minute left. Maybe we should wrap it up now.
Yeah. Well, thank you, Rusty. And yeah, we'll just close out these questions now. Thanks everyone for coming. We'll have another webinar next month in May, and that's going to be the second Thursday. That's May 11th. So we'll see you there. Thank you.
Okay, thank you so much, everybody. Have a good day. Thank you.